Good morning and welcome to Physics Studio. What I'd like to talk about today are two aspects of oscillating systems called resonance and natural frequency. We're going to briefly lay out the conceptual relations between the two, and then we're going to look at a bunch of examples. And I think once you get this down, you're going to start to see that resonance is something you encounter all the time in life. So anyway, resonance as an aspect of an oscillating system is where you get a rise in efficiency and energy. When an external driving force is at the natural frequency. So you've got an oscillating system, and supposing it's at equilibrium, it's just going to sit there, right? You can disturb it with a single disturbance and it will start to oscillate, but you can also give it a periodic disturbance. And if that disturbance is at the natural frequency of the system, it'll suddenly snap into this highly efficient operation, and it's really easy to add energy to it. So those are the two things you look for to recognize a resonating system. Now, that can be good because it's efficient and often beautiful. But resonance can also be bad because you can get dangerous energy levels. Now, natural frequency is something that any oscillating system has, or any system that's being, put through any kind of periodic motion. And natural frequency is a function of two things. One is what I'll call the mass characteristics, and one is called, let's call it the nature of the restoring force. By mass characteristics, I don't just mean the amount of mass, but also the relation of the parts of the object, the masses to other parts of the system. Restoring force means, whatever that is, elasticity, gravity, that kind of thing. In general, if you raise the mass characteristics, the natural frequency goes down. And if you increase the restoring force, the natural frequency goes up in the system. And so as we look at a bunch of examples, I want you to think about that. Think about how you recognize when the system goes into resonance. And secondly, how the mass characteristics and the restoring forces affect the natural frequency. So example number one is going to be our familiar pendulum. And our pendulum is at equilibrium right now, and it's got a natural frequency that depends on the mass characteristics, which in this case is how far away the mass is from the pivot point, and the restoring force, which is G of the Earth at the Earth's surface. Now, if I disturb this, it'll start oscillating at a certain period. And there's nothing I can do to change that. I can disturb it more. It's still oscillating, and if you do careful experiments, you'll find the time for one cycle is the same, right? It's covering more distance, but it covers it faster, and so that those effects cancel out. So there's nothing that I can do to change that natural frequency, no matter how hard I push. Now, the second aspect of my disturbing force is if I disturb it periodically at the natural frequency, it starts to gain energy. And you know this because you've been on a swing set, right? If there's someone behind you and they want to get you to swing higher, they start pushing, right? They push right when you come back and then push, right? And so that their periodic driving force is the same as the natural frequency. If I try to apply a periodic force that isn't at the natural frequency, I'll just start to mess up the motion. right? And so you get that disorganized motion if your driving force is not at the natural frequency. As soon as you hit the natural frequency, though, it starts gaining in energy and operating more efficiently. Now, I want you to think about another example, and that would be musical instruments. And musical instruments are essentially devices for the controlled change of natural frequencies. So if you have, for example, a guitar, you have 6 strings, right? And the bass strings are heavy and the higher frequency strings are light, right? So as the mass goes down in the string, you get a lighter and lighter string, you get higher frequencies of sound. You can also notice if you want to tune the string, you tighten it, right? And by tightening the string, you're increasing the restoring force, which causes the natural frequency to go up. You can think about sequences of instruments, for example, from the bass to the viola to the violin, right? As the instrument gets larger and larger, the sound goes down. The natural frequency gets lower and lower. Wind instruments and woodwind instruments, brass instruments, etc., they all control the length of a column of air that's vibrating. And that's got a natural frequency too, and that can be adjusted by pressing buttons or covering holes and that kind of thing. Let's look at a couple other examples. Okay, I've got a blade of grass here, and if I take that blade of grass and I pin it between my thumbs and I stretch it a little, right, I've produced a restoring force, and if I make this column of air go through at the natural frequency, there's a sudden rise in energy. Similarly with whistling, I can change the shape of my mouth, etc., and tighten, various things. And at a certain point, you get resonance. If I blow the air through at the wrong speed, it won't resonate. But once you hit the natural frequency, it resonates. Okay, this is a ruler, and along the entire length of this ruler, the elasticity is the same. Right, but when I have it like this with half the ruler over, I have a lot of mass to move. That's the natural frequency. If I pull this in, the restoring force is the same, but now there's less mass. Higher natural frequency, and you can see I can just... Okay. Now, this is a crystal goblet. You may have these at home, and you can do this. If you wet your finger, right, and eliminate a little bit of the oils, and then just run that at just the right speed, right? The friction from your finger begins to oscillate the glass, and when you hit the natural frequency, it will resonate. And if you have any kind of crystal at home, you can do this as well. Now let's see what else we can find that will resonate. I want you to let's just think about this one. I think probably all of you have jumped rope or seen rope jumping. Now, if you have 2 people, right, each holding one end of the rope, and they get into a rhythm at the natural frequency, and suddenly the rope swings very easily. If one person at one end starts going at a different frequency, the rope will go into disorganized motion. So same thing. A swing is a great example of that. You can only drive the person on the swing at the natural frequency. That also illustrates the danger, because when you hit that, it becomes easy to add energy, and you can imagine and may have experienced the swing getting into dangerously large swings. So Another example is earthquake prevention in buildings. You might think that buildings in, say, Tokyo or California, where there's a lot of earthquakes, are built to be very rigid, but that wouldn't work because it would just, it would essentially break during an earthquake. What happens is the bottom of the building is made flexible so that it can move, and there's disposition of masses in the building so that the natural frequency of the building is not something that's in the likely range of seismic frequencies that you would experience. And so if the earth starts shaking underneath it, it's off the natural frequency and it just experiences small amounts of motion. So that's your basic introduction. Look around for that. Let's think of another example. If you have a large animal like an elephant, it makes a very deep noise. What kind of animals make high-pitched noises? Right? Small animals, birds, insects, etc. And if you go up to a door and you hear a yipping kind of barking, what kind of dog are you going to imagine behind the door? But if you hear a woof, that kind of a bark, you're going to imagine a different kind of dog. That's your natural understanding of natural frequency. So anyway, today work through the rest of the sections 13.1 and 13.2, and I'll look for your lesson checks. Have a great day.